Okay, it is my great pleasure, and I'm very happy that I can introduce Bartomeu Monserrat to all of you. He did his PhD in the Cavendish Laboratory in Cambridge under the supervision of Richard Nitz. Then he did a postdoc at Rutgers with David Vanderbilt, and now he has a faculty position in Cambridge and his own group. He also has several prizes. He won the Psyche Volker Heine Prize in 2018 and the Maxwell Medal in 2021. He's an expert in phonons and topology, and today he's going to talk about multi-gap topology of phonons. So, Tomeo, whenever you want.
Thank you very much, Maia, for the kind invitation to speak today and for the kind introduction. So, welcome. So today I'll talk about multi-gap topology of phonons. This is a rather new topic for us. It's the first time I give this talk, actually, so it's a bit rough. And the first half of the talk, I'll describe what I mean by multi-gap topology. And then in the second half of the talk, we'll see how we can apply that to phonons. And I'll try to argue that phonons are perhaps an ideal platform to study this phenomenon. So some of you may be familiar with band crossings, which have become very popular in recent years in the study of condensed matter systems. So you have two bands crossing, forming a band node. These are sources or sinks of vary curvature. They're generally present in 3D systems without inversion or time reversal symmetries. They come in pairs of opposite charge, which can annihilate and create together. And there is a growing body of work on these compounds. If these crossing points happen near the Fermi surface of an electronic system, then you have what you call a Weyl semi-metal. This will be the Weyl points, sinks and sources. This is one of the first experimental observations of this phenomenon in a real compound. And as any topological quantity, the bulk topology, in this case, these crossing points, is associated with the surface state. In this case, these Fermi arcs that form between the projections of the bulk crossing points on the surface. And what I'm showing there from this paper from a few years back is a comparison between the calculated surface states and those measured experimentally with ARPES that sort of confirm the presence of this topological crossing points in the bulk of the system. Now, much of this phenomenon has been studied in electronic systems, but other quasi-particles also have band dispersions that can also host analogous phenomena. So us and others have done some work in trying to observe these types of topological crossing points, for example, in phonon systems. So this is an example where we looked at tetragonal barium titanate under some external parameters, which in this case happen to be photoexcitation. And this is a typical phonon dispersion, and we found a number of interesting topological features, including these Weyl points. And although they, in principle, come in pairs, when you add crystallographic symmetry to the system, then you may get something like, in this case, 4 pairs of Weyl points. And again, these crossing points have also been observed in phonon systems experimentally and have similarly associated surface states, for example, compared to electronic systems. Something interesting that you may want to do with these is to actually manipulate them by changing some external tuning parameter. And here we looked at how changing the photoexcited carrier density, we can create this, for example, along this line, and then they migrate along the Brillouin zone, and they meet another partner and annihilate when they come together. So you can do various of these things, and this is an example using photoexcitation to manipulate them, but you can also imagine using other things like strain, pressure, temperature, and whatnot. Anything that you can tune externally that affects the band structure of the system or the phonon dispersion of the system, you can then use to manipulate the topology of the system. In the context of this talk, I'll refer to this sort of phenomena as single gap topology. So what I mean by that is that we have two bands, and if they don't cross, they form a gap, and occasionally we'll have crossing points along this gap, But essentially, you can imagine that this is the gap, and there happens to be a point where they cross, but otherwise, it's a single gap. So you can describe all of these phenomena essentially with a two-band model, if you want. And for this reason, in this context, we'll call that single gap topology. And what I want to talk about today is how we can go from this single gap topology to what we call, in this context, multi-gap topology. So the first thing I'll do is I'll introduce the ideas behind multi-gap topology. As I said, this is a rather new field for us. We got interested in this through two collaborators, Robert Jan Slager and Adrian Bohon. And what we've done essentially, we come from a DFT background, so what we've done is we've teamed up with them and tried to see how we can make this happen in real materials. So that's the story I want to tell you about today, essentially. Okay, so the simplest setup that you can have for multi-gap topology is rather than a two-band system, is a three-band system. Okay, so here I'm writing a three-band Hamiltonian in the energy basis. And just to define some notation, so we'll have three bands, and we're just going to order them in energy. So I'm going to call them E1, E2, and E3. And then we're also going to define two gaps. So delta 1 is the gap between bands E1 and E2, and delta 2 is the gap between bands E2 and E3. And in general, well, that's the definition of the gap. It's you could have some crossing points in these gaps, or just be like that. And the other key aspect in multi-gap topology is that we're actually going to work with real Hamiltonians. So this is the constraint that we have. And in order to ensure that the Hamiltonian is real, essentially we have to have some symmetries present in the system. And it happens to be the case that if you have C2T or PT symmetries, then, for example, on the C2T invariant plane, then the Hamiltonian can be made real. Okay? So in general, much of what I'll discuss today applies to all these cases. But for concreteness, what I'll do today is I'll focus on two-dimensional systems with C2T symmetry, and then it's just easier to visualize everything. But this could also be a C2T plane embedded in a 3D system. Okay, so that's the setup. What we're going to be interested in today is in essentially crossing points between this multi-gap setup. Essentially, very briefly, I won't go in detail into that, but very briefly, because you have these three real eigenvectors, you can define an orientable frame, and the topology associated with that can actually be described with the quaternion group. So what that means in practice is that when we have these three bands like this, and they form crossing points as shown in this example here, then we can characterize the crossing points in the first gap by plus minus I, and the crossing points in the second gap by plus minus J. And some more notation. For clarity, what I'll do in the code is I'll define crossing points in the first gap by squares, and crossing points in the second gap by circles. Okay. And then when these crossing points have positive charge, then they'll be filled squares or filled circles. And when they have negative charge, they'll be open squares and open circles. Okay, so that's notation we'll use. And what I want to do now is I want to explore how this quaternion group comes into this setup. The first thing we can see is that when we consider these charges for a pair of nodes in the two different gaps, then that can be described by the quaternion charge K, because Ij is equal to K. When we have a pair of nodes in the same gap, then if the pair of nodes has opposite charge, then they're described by the +1 entry. And what that indicates is that these nodes can annihilate because they have opposite charge. Now, if notice I've flipped the sign of those, therefore they're open. If the two nodes in the same gap that you calculate together happen to have the same charge, then they cannot annihilate. And if you do the multiplication of the quaternion group, then you get -1. So this is just the example I have here, but you can go through the math, and minus J would also give you -1, J would also give you -1, and so on. So this is how we do this. And an interesting thing here really is that the quaternion group is non-abelian in the sense that I, j, and k don't commute. So this is something interesting that we can exploit because imagine that we start with this setup here. What I have here is momentum, energy against momentum, the one I had earlier. And I start with 2 nodes of opposite charge on gap 1 and 2 nodes of opposite charge on gap 2. And here I'm plotting the exact same setup, but now rather than looking at energy versus momentum, I'm just looking at the 2D Brillouin zone, and I'm plotting at the location of the Brillouin zone where those nodes are. So it's exactly the same situation as here from a different point of view. And then I imagine that I braid one node in one gap around the node in the other gap, indicated by this operation here. And mathematically, that's represented by the conjugation property. And if you go through the mathematics of the quaternion algebra, then you see that I turns into minus I. That's a reflection of the fact that it's non-abelian algebra. And the end result is that now by braiding this node around this node in reciprocal space, we flip the sign of these 2 nodes, and therefore we start with 2 nodes in both gaps that can annihilate, and we end up with 2 nodes in both gaps that cannot annihilate because they have the same charge. So this is roughly how the setup for non-abelian braiding of this multi-gap topology works. However, when we want to actually do calculations with this stuff, it would be extremely tedious to go through all of these and try to characterize every crossing point with the various quaternion charges. So what we really want to do is we want to have a much more flexible way to study this phenomenon. So this is where the Euler form comes in. So for those of you who are familiar with topology, then you probably know that for complex Hamiltonians, then the Chern number, the Berry curvature, and so on are the relevant concepts to characterize the crossing points in those cases. So the Euler form is essentially the real counterpart of that, if you want, and that allows us to do the same for these real Hamiltonians and these multi-gap band crossings. So here, just a few definitions, and again, for those of you familiar with Berry curvatures and so on, you'll recognize most of these formulas pretty much. So we have the Euler form here, which, so again, the Berry curvature, for example, of a 2-band system can be defined for a single band in there. So here we have a 3-band system, and the Euler form is defined for 2 bands in that 3-band system. So, and the notation I'll use is the Euler form of band n is really depends on the eigenvectors of bands n and n+1 for both of them. And then you also have the Euler connection. And then what we can define is this patch Euler class, which is a number that you get by essentially integrating this Euler form across some region of the Brillouin zone. I label that region by this D here, and it also has a boundary term there. But that's essentially the mathematical formula that defines this patch Euler class. So again, those of you familiar with complex Hamiltonians, then will recognize the format list of most of these formulas.
Is that number an integer?
Okay, so I'll get into that in the next slide. So if the patch covers the entire Brillouin zone, so by delta I mean so you imagine you have a 2D Brillouin zone and you define a region of integration in there. So if that covers the entire Brillouin zone, then it is an integer. Okay, and what that tells you is that there are, and we'll get into a moment about gauge freedoms. So for now, we'll just say, okay, the absolute value of that integer tells you the number of pairs of stable nodes in the Brillouin zone formed by that 2-band subspace. Okay, so it's an integer that tells you how many pairs that cannot annihilate you have in there. Okay, but you can also define a patch that doesn't cover the full Brillouin zone. Okay, so in that case, And we just call that a patch rather than the full Brillouin zone. And in that case, chi-n can be an integer or a half integer. Okay, and we'll get into a moment in a bit more detail about this. And what that tells you then is that in that patch, there are, again, because of the gauge freedom, there are 2 times absolute value of chi-n stable nodes within the patch. Okay, and in a moment, we'll look into a few examples of that. But I hope that answers your question. Okay, so let's see what that means. So again, I'm looking here at a 2D Brillouin zone, so K1, K2, and I happen to be looking at the gap. If you remember my notation, the gap delta 2. So I have 2 gaps, delta 1, delta 2. I'm looking at crossing points in the gap delta 2, which I labeled by J's or by circles. Okay, if you remember my notation at the beginning. And here I just happen to have two nodal points of opposite charge, so plus J minus J. And then this gray area here is my patch. Okay, so you can just define it as you. It could have any shape really, as long as it just captures those 2 nodes. But let's say it has this sort of rectangular shape. And then in this particular case, if I calculate the Euler class, which again I label chi2, because this is sort of between bands 2 and 3, again, notation, then essentially that Euler class of 0 tells me that these nodes can annihilate. Okay, so I have 0 stable nodes in my patch, because although I do happen to have 2 nodes, they can annihilate, so they're not stable. I have 0 stable nodes in my patch. By contrast, if I get chi2 equal to -1 in this case, the absolute value of that is 1. So that tells me there is 1 pair of stable nodes in the patch. So they both have the same charge, so they cannot annihilate. Okay, but so in this case they're integers. But I could also do this. I could define a patch around a single node. In this case, say a minus J node, and then my overall form would be -1/2. So that tells me, in fact, that there is a linear node in that patch. Okay, and I could also have a single node and get an integer Euler form, and then that would tell me that I have a quadratic node that you can think of as a superposition of 2 linear nodes. And for that reason, I'll actually represent that as 2 concentric circles, one inside the other. And if you remember, then the -1, when we work with the quadratic group, meant you cannot annihilate them, and they're stable. They just happen to sit on the same points. Is that roughly clear from? Okay. So that's essentially how we're mathematically going to characterize these normal points. And something I've already alluded to, but I haven't really gone into, is the gauge dependence actually of what we have. So we're used to, in complex Hamiltonians, to have a phase gauge dependence. Now here we have real Hamiltonians, so the phase gauge dependence becomes a sign gauge dependence now. And actually, I haven't gone into that, but what we use oriented frames. So what that means is that we have to switch 2 of the vectors at the same time to keep the same orientation. Okay, that's just a detail in a sense. But essentially, what that means is that I can make a gauge change from this set of 3 basis vectors, and I can flip the sign of 2, and I get the same physical state. Okay. What happens is that when I do that, then the Euler class also flips sign, and so does the node charge. Okay. So for a node taken in isolation, the actual sign of the Euler class or of the node has no physical meaning. It's a gauge-dependent quantity. Okay? And if you do that and plug that into the formula, it just comes out. So it's relatively easy to see. What has physical meaning is the relative sign between 2 nodes. The relative sign between 2 nodes is not gauge-dependent because it tells us whether those nodes can be annihilated or not, and that is a physically well-defined quantity, so it's not gauge-dependent. So what we're going to do really to characterize this multi-gap topology is we're going to try to build global topological configurations while taking this gauge dependence into account and trying to extract these physically meaningful things, which is whether nodes can annihilate or they cannot annihilate. And I'll show you in a moment. It essentially becomes a puzzle. It almost becomes a game to build these global topological configurations, and we'll see in a moment how we actually do that. So before we do that, I want to introduce this final concept, which is Dirac strings, which is a gauge-dependent quantity, but it's very useful for us to visualize what we're doing, when we're choosing the various local gauges in the system to build the global topological configuration. So bear with me with an extra moment about the Dirac string. So essentially, when we have a node, there is if you build a loop around the node, then if there's no, then you'll get a pi-Berry phase, right? And that means that there's a line you have to cross where the gauge is. Essentially, there's a pi disinclination line between 2 points because of this, because of the fact that you have nodes. So when you loop around them, you get the pi-Berry phase. So you can think of this as across this node, then the gauge is not smooth. So so what we have then is we can visualize this to the Dirac string. So we could imagine that we have these 2 nodes, and we can build this Dirac string that tells us that across this line the gauge is not smooth. And of course, this is a gauge quantity, so it doesn't have to be here. I could throw it anywhere I want. And what we're going to do is we're going to exploit this to actually build this global topological configuration that I was mentioning. But in order to be able to do that, essentially, although for a given local region, the gauge choice is arbitrary, because of the physical meaning of whether nodes are stable or not, you have to worry about the relative gauge choice that you make between all the nodes. And that's what we're going to use to build this global topological configuration. And these Dirac strings essentially allow us to keep track of what we're doing, and we'll see in a moment how we use them. And essentially, it all boils down to a set of rules that I'm going to define now that we can just use when we build this global configuration. And so what are these? We call these the Dirac string rules, and they're as follows. So when we have linear nodes in a given gap, then because they have a pi-Berry phase, they must be connected by one of these Dirac strings in pairs. So that's rule number 1. You can think of a quadratic node as 2 linear nodes on top of each other. So you could imagine that they have like an internal Dirac string. So those don't need a Dirac string connected to anything. Rule number 2 is that to be consistent with the frame charge of the other gap, then the sign of the frame charge of a node in one gap must change when it crosses a Dirac string connecting 2 nodes in the neighboring gap. So what does that mean? And you can actually visualize this in 2 ways. So the first one is moving the nodes. So we have 2 nodes in the gap 2 and 2 nodes in gap 1. Okay, and in this particular example, they both the 2 nodes in gap 2 happen to be of the same sign, so they cannot annihilate, and the 2 nodes in gap 1 also happen to be of the same sign, they cannot annihilate. And then I draw these Dirac strings between the nodes in each gap. So then what I could do, for example, is I could move this node in gap 1 across here, across the Dirac string in gap 2. And then to be consistent with the gauge choices that I've made in the various gaps, then the second Dirac string rule tells us that then I need to flip the sign of the node that crosses the string. So in this particular case, this flips the sign. Now, physically, nothing has changed, because if I actually wanted to annihilate these 2, I would have to recross this string somehow, so I would flip the sign again, and I cannot really annihilate. So I can represent, so these 2 situations are just, if you want, different gauge choices of what I'm doing, but they represent the same physical quantity. And I can do the same by moving the string if you want. So I can fix that and just move the string across. And again, if I move a string across the crossing point, then I need to flip the sign. Is that roughly clear? Yeah.
So if I understand correctly, in the one in the bottom left,
yeah,
you would now move the green ones, right? So the green circles to the right. Yeah, that one.
That one?
Okay,
yeah.
So yeah, or the right one to the left, so that it crosses the string.
Exactly.
And then it changes.
Exactly. So this one would. So if I go from here to here,
yeah,
then this one changes. Crosses the string in the other gap. So it changes, it flips sign. And And what you've done essentially is a braiding, actually. So you flipped the signs. You braided one node around the other, right? You braided one node around the other, and the braiding flips the sign physically.
So now you can annihilate them.
Exactly, because you braided the nodes.
Okay, because just a braid. Okay.
Does that make sense? So you flip them, so you've actually braided them. So in that case, you've actually done a physical process of going from two nodes that cannot annihilate to two nodes that can annihilate. So that's, you braided them together.
That's a braiding.
Does that make sense?
Yes.
Yeah.
One question. So just to see if I understand correctly the Dirac string thing. So you said that the Dirac string things like a line where you don't have like a smooth gauge in the sense that, but I understand that you don't have a smooth gauge when you, since you are understanding like the J and minus J like a frame orientation change, as you said. So therefore, when you have minus J and minus J, you have a smooth gauge or you don't. And when I understand that you don't have a smooth gauge between I and minus Y, or minus I. So between charge and anti-charge, because you have, I understand that you said that the charge doesn't have meaning in the sign because it can be changed with the gauge. But when you have the same charge in both sides of the Dirac string, you also don't have a smooth gauge. I don't know if I
explained that. So the fact that you don't have a smooth gauge,
yes, between
you can look at that just depends on a single node in isolation, right? So you have a single node in isolation, and you loop around, you calculate on the loop around that single point.
Yeah.
Then if you get, say, a pi-berry phase, that's already telling you that there is discontinuity, right?
Yeah.
So you can define it with a single node, and then all the Dirac string is telling you is that it's connecting two different nodes that have that, but it doesn't matter whether those nodes are, plus or minus I.
Okay.
Is that your question?
No, maybe I over. So yes, okay. Maybe I understood wrong the concept of the answer. I think now I
okay.
It's simpler than what I thought.
Okay.
Or you made how.
Okay. And then example number 3 is essentially the fact that these are gauge objects, so you can actually reassign how they connect without changing the fit. So these are all equivalent configurations for the Dirac strings. You have freedom in how you set them up. You then have to keep track of whether they cross nodes in other gap sorts. Okay, so this may have sounded rather abstract, but and it is. But what we'll see actually in a moment is we'll see actually an example of how we put this in practice and how we can use that to actually define the global topological configuration of a 3-band system with multiple crossing points. And essentially what we do is we do this like a puzzle. So we calculate the patch Euler class, say a pair of nodes, which does have physical meaning, for example, in terms of whether they can annihilate or not. And then we combine that with the Dirac string rules to then build the whole topological configuration that is consistent throughout the entire Brillouin zone. And essentially what you have to do is you start with one, and then you start adding the pieces to make them consistent relative to the first one that you built. And that's why we call that a puzzle. And in that way, you can build something that with those particular choices of gauge that you've made, gives a topologically global configuration. You could make other choices, but they should all lead to the same physical configuration at the end, because you cannot change the physics. So as I said, we'll actually do an example of this in detail, how we actually build this with a concrete example. So hopefully that will also become a bit clearer then, what we're doing here. But before I go into that, I just want to mention that this is all rather abstract, three-band Hamiltonians and crossing points and so on and so forth. What we really want to do is we want to see this in real materials. And that's where actually we came into this collaboration that our background, the FT modeling of materials. The obvious place to start is in electronic, before I go into that, essentially when we want to do this in real materials, all we need to do is we need to evaluate these things for real materials. So we can do this in DFT, for example. So you have DFT, you have your bands, and you just plug in eigenvectors in these equations, you calculate these things. And of course, this could be electronic bands. This could also be phonon bands, exciton bands, whatever you can think of, where you can get the eigenvectors out and build this quantity. So the obvious first place to start is in electrons. Okay, so there are a few proposals of materials that may exhibit multi-gap topology in electrons. So this one here is not our work. So that was interconium telluride, and they proposed that we could observe this phenomena with really large uniaxial strains in that compound on the z-axis. And in that particular case, the nodal points happen to be about 50 MeV from the Fermi level. This down here is our work, where we look at a slightly different compound, and we do observe this across the phase transition in this compound that goes from two various symmetries. These are both, this in particular is a known compound, this is a known phase transition. We just characterize that phase transition from this point of view. And in this particular case, nodal points happen to be within 200 MeV of the Fermi level. So there are, what I'm trying to say here is there are a few proposals of electronic systems where you could observe this phenomenon, but it hasn't yet been observed experimentally. And I think there are various reasons for that. So there aren't that many examples. Part of it is because electronic systems have a Fermi level. So you have to essentially be lucky to find the three bands that exhibit this interesting phenomena to exactly be near the Fermi level. And this is a place where some of the work being done here could become really handy because we have large databases with very well characterized electronic bands. But for now, there are just very, very few examples. So this hasn't actually been observed experimentally. Another difficulty is that even if this is really close to the Fermi level, then fundamentally the Fermi level is to be one gap or the other. So if you want to explore the full phenomena across the three bands, then that sort of suggests that electronic systems may not be the ideal platform to do this, because the Fermi level is here or here or here. But ideally, you would like to explore what's going on in this whole three band system. So electrons may not be an ideal platform to study this multi-gap topology for this reason. I think it would still be very interesting to find this phenomenon in electrons, because electrons are charged and they have some very nice spinful and so on, have some very nice properties. But we thought that at least to set off the sort of experimental study of this field, then phonons may be a better way forward, because phonons, unlike electrons, don't have a Fermi level. They're bosonic excitations, and therefore, in principle, you can access the entire spectrum. There's no Fermi level, so it doesn't matter where they are in the spectrum. As long as you have these three bands, then you can, in principle, access. So that was sort of the key suggestion. And all we really have to do then is here run using the electronic eigenvectors, which is the phonon eigenvectors. But otherwise, things carry through in the same way. So that's what we did. And what I want to do to finish off is just to show you a few examples of materials where we think that we could observe these. We actually have a proposed experimental signature to observe this phenomenon occur. So the first example we have, so far we've actually looked only at monolayer systems just because it's easier conceptually. But in principle, all you need is those various symmetries that we discussed, and they could be embedded in 3D. And in fact, the examples here for electrons, for example, this one that we did is a 3D material where we have a few C2D invariant planes. So these things happened in these planes, but they're still embedded in the 3D system. For phonons, we just decided to start with 2D systems just because I thought it would be easier to start with. So the first one is this monolayer aluminum oxide. It has a honeycomb lattice, the oxygen atoms form a Trigonal lattice. As a space group, it has C2T symmetry, and there are 5 atoms per unit cell. And this is what the phonon dispersion looks like. So 5 atoms per unit cell, 15 phonon branches. And the 3 bands that we're going to focus on are these 3 bands up here. And as we'll see, it's useful because they're completely isolated from the rest. So we do have a true 3-band system if you want. So we can explore this physics without getting stuff from other bands interfering with what we're trying to do. They happen to be in the material around 30 to 35 terahertz. Okay, so this is just to zoom in of this in here. And what I want to do now essentially is I want to to go through building the topological configuration, the global topological configuration characterizing the multi-gap topology of this three-band system, applying these rules that we've discussed, just as an example of what we have. So, so what I have here are the bands, the various EREPs, and the crossing point. So essentially, there is a crossing point along gamma m between bands 1 and 2, which in reality, I think they are bands 13, 14, and 15. Okay, so we'll call them 13, 14, and 15. And so there is this crossing point between bands 13 and 14, or 1 and 2, if you want. Then there is this crossing point at K and this crossing point at gamma. And these two crossing points are in the second gap, not in the first gap. Okay, so this crossing point is in the first gap, and these two are in the second gap. And that there is just a view of the 2D Brillouin zone of the same thing. And bear with me because just for convenience, we've put it in a slightly weird way. So these are the K points, okay? These are the gamma points, and these are the M points. Okay, so I know usually you have the gamma point in the middle. Here we have the K point in the middle, but hopefully it should be clear otherwise. So just to make sure, so we have a crossing point in green at the K point, here, 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 there. We have a crossing point in yellow at the gamma point, here, there, there. And then we have this crossing point along the gamma n direction, so along the gamma n direction. Okay, hopefully it's clear. Okay, so then what we do essentially is we want to characterize these crossing points from for this three-band system. This can be described in the real Hamiltonian because the system has zero dissymmetry, so you just have to make an appropriate rotation to make it real. We've done that. And then the first thing we do is we build the puzzle. So the first thing we do is we look at all individual nodes. We build a patch around every individual node, and we calculate the patch Euler class for that patch. So patch number 1, just the patch around the first node, which you remember was gamma, and we label that K14 because remember it's band 14 and 15, or you can think of it as chi2, and we get -1. So if you remember, that means that this is a quadratic node. So that's why, if you remember, we represent quadratic nodes as the superposition of two linear nodes, so two concentric circles. And you also remember that in the second gap, we had circles rather than squares, which we had in the first gap. So that's going back to the notation we have. Then the second point is K here. We can build a patch covering that nodal point. And in this case, we get -1/2. So that's a linear node. Again, it's between in the second gap, so it's still a circle. And then the third one is patch number 3, which should be at here, is this one. So we build this patch here, and we find, so that's chi13, because it's in the first gap, and we get +1/2, so again, it's a linear node. So we have a square because it's in the first gap. Okay. Now, once we've done this, then we build. Well, gamma point we can just straight away. Gamma point is the same, so we can straight away realize that those are also quadratic nodes. And then what we do is we build the patch across every pair of linear nodes. Okay. So here are 3 new patches. So patch number 4 is this one here. And this one contains 2 linear nodes at K. And for that patch, we get K14 because K is between in gap 2 equals 0. So what that means is that those 2 nodes are not stable, so they can annihilate. And now we have a choice. We can either have them of opposite charge, so they can annihilate, or we can have them, and that's the choice we've made, we can have them as the same charge, but then crossing a Dirac string in another gap. So now when they come together, they would cross that, flip the sign, and then annihilate. Okay? So these are 2 equivalent choices that represent the same physics, but we just make this particular K choice here to represent it. Okay, so that's patch 4. Then patch 5 covers these 2 points along the M line, and we get +1. And then patch 6 covers these 2 across the M line, and we get 0. And then we build the corresponding signs of the points, taking into account the various Dirac strings that we decided to build in this particular way for convenience. We could have made many different choices of this, but that's how we build that. Okay.
One question.
Yeah.
Green nodes don't care about green Dirac strings, no?
No, because so it's you have to cross a string in the other gap. Yes. Okay, so that's the global topology configuration that we do exactly in this process. And what's important, what's physical, is whether nodes can annihilate or not together. The particular choices of how we connect them and what particular frame charges signs we choose with them, and that's just our gauge choice. But physically, it should give the same physics eventually. Yeah.
So out of the nodes in gamma, there are no strings because the very face is 2 pi around that node. Or...
Yes, so you can think of it as an internal string if you want, because it's 2 linear nodes, one on top of each other. Yeah. Okay, and then what we usually do is we do a consistency check at the end. So we pick a final patch just to make sure that our choice makes sense. So in this particular case, we choose patch 7, which covers these 2 nodes, and we find an Euler form of minus an Euler class, excuse me, of -3 halves. So, and that's consistent because this is a linear node, which is open, so it's -1/2, and that's a quadratic node, which is -1, so -3 halves. So it's consistent with what we think is the topological configuration of the system. Okay, so that's how we build this. And then the interesting thing really is to manipulate this. So to change some external parameter to see these nodes physically move around, and therefore maybe induce braidings, transferring, flipping the sign of the charges, and so on. But once you've built the topological charge of, say, the starting point, then it's easy to move on from there because you have a tuning parameter that continuously moves these points. Then all you have to do, you have to keep track of what they cross, what they don't cross, and see how you flip signs and so on and so forth. So that's what we did then. In this particular material, what we did is we manipulated the phonon dispersion with electrostatic doping. So you imagine you put a gate or a voltage gate or something, and you essentially move the Fermi level of the system up and down, and that affects the phonons. And therefore, and what I have here is my tuning parameter, which happens to be the amount of extra of extra electrons in my system performing the unit. And that modifies the phonon dispersion just because you're populating or depopulating certain bonds. Therefore, the force constants change, and therefore the phonon dispersion changes. And then you can see as you tune that how these nodes evolve, and you can try to understand it in these terms. So this here essentially starts at -0.06, but essentially it is the same that we had here at 0. Just it has evolved smoothly, nothing interesting has happened. But as we do that, then what happens is that those points that we had along the gamma m direction, which started off here, have started moving. Okay, physically moving now. And if we look at this, what happens is that these 2 here have the same frame charge. So they will actually not be able to annihilate if they emit. Same here. And here, the same will happen actually, because although naively they have the different frame charge, they actually have to cross a Dirac string in the other gap for them to be able to touch. So in fact, physically what happened is that those nodes at the gamma n direction will go towards each other, and then when they meet, they will not be able to annihilate. And that's exactly what happens here. So they meet here, they cannot annihilate, so actually, in this particular case, they bounce off each other, and they start moving along the k gamma direction, I guess. And then we represent them like this, like this, like this. Okay. As we're doing that, other pairs of nodes actually appear. So this and this, and they also start moving together and so on. And what you can do is you can build this evolution by just evolving your initial global topological configuration and smoothly connecting the various terms. In this particular case, we started with that, and then we have this rather complex evolution. You have to really sit down and work through all of this detail. And at the end, beyond beyond this amount of extra electrons in the system, you end up with a relatively simple setup in there. And throughout this process, multiple braiding events have occurred. Now, the braiding is not as simple as what we had in that example, just one around the other, because here we have to take into account that in real materials, we have extra things, which are, apart from the C2T symmetry that makes sure that we have a real Hamiltonian, we also have crystalline symmetries. And those mean that many of these points, for example, move along high symmetry lines, and so on and so forth, or we have multiple copies of them. So that just complicates the analysis somewhat, but as we'll see in the next example, could actually provide a very simple experimental signature. Okay. So in principle, one could probe this by measuring the phonon dispersion of these systems, maybe with like neutron diffraction or something. But those are all rather complex experiments. So we think we have a much simpler signature that one could use to at least try to identify some of this to start with. And that's the second example I want to discuss, which again, monolayer, similar structure of silicon oxide. So this material has also been grown experimentally. It's an interesting monolayer. It's not a freestanding monolayer. It's actually a material that has to be grown on the substrate. So I know what you want to call that, but it's a material that, although it's 2D, it's not freestanding. So you have to grow it on the substrate because it's not saturated. So in our particular simulations, we essentially saturated with, passivated with hydrogen atoms. In reality, you can grow it. People have grown it in a variety of substrate, and it can actually sustain quite a lot of strain. We're actually going to use that to go to a regime where we can see this braiding again. But then the game is the same. So before I go on, this is the phonon dispersion in this case. We have those high energy bands there, which correspond to the hydrogen passivating atoms. And then the bands we're going to be interested in here are these here. So we have, first of all, this group of 3 bands up here. And then it may not be completely clear, but we have another 2 groups of 3 bands. So we have another group of 3 bands here and another group of 3 bands here. And what happens is that, so this is a zoom in of that region at 0 strain. And in this particular case, we play with a perpendicular electric field to the plane. Those colors there show the perpendicular electric field. And if you look here at 0 strain, then we can see that as we change the electric field, the bands change somewhat within each of the 3 band subspaces, but not very interesting manner. However, if we apply some strain, then what happens is that, first of all, the 3 bands in this group 1 become closer together, and then the electric field changes can actually induce band inversions and braiding. And the other interesting thing that happens is that bands from group 2 and 3 also come together. So you actually have a 6-band subspace. And of course, all the ideas we've been discussing have been in the context of 3 bands, but this generalized to more bands. And this is, we think, is the first example of, in this case, 6 bands coming together, and the braiding that happens actually between just 4 bands, but still more than 3 bands. But then you can play the same game. So I won't go into the details of the various global topological constructions and how they evolve. But what's interesting in this case is that, so here, as I said, the braiding is with an electric field, and you could follow this and so on. What's interesting in this case is that because of the crystalline symmetries, the braiding actually collapses to the gamma point. So in reciprocal space, rather than seeing a physical braiding like a node moving around the other, it all collapses to the gamma point. So essentially becomes 2 nodes crossing over at the gamma point. So it's a band inversion at the gamma point. Something very similar happens for the sort of 6-band subspace, where group 2 and group 3 sort of merge together here. And again, all collapses to one of the braidings collapses to the gamma point. And that's what takes us to the experimental signature, because you can track phonons at the gamma point with Raman spectra. So, so all we have to do really is we start with our 2 Raman active modes at the gamma point, and the braiding just happens to be a band inversion of those poles at the gamma point. So you have to track the Raman of this system and see how, as you change the external parameter, the two Raman peaks cross and then flip. And that's for the group of 3 bands that we started with, and that's the same for the group of 6 bands that we had there. So that's what we propose to be an experimental signature to observe this braiding in this compound, which Raman is something really accessible. So it should be something easier than, say, neutron diffraction to look at braiding in a whole Brillouin zone. So it should be, we think, a first good proof of principle of this phenomenon, which is yet to be observed in real materials, that this braiding can indeed occur in real materials, in this case, in photons. Okay, so this is all I really wanted to say. Before I finish, two very quick things. The first one is that I have two openings. So one postdoc and one software developer. The deadline for applications is 20th of January. And there'll actually be two more openings at least coming up in the next few months. So if anyone is interested, please go ahead. We have a group of international students and postdocs in Cambridge, and we do a variety of things. But yeah, if anyone's interested, also feel free to drop me an email for an informal discussion. And the second point I want to mention is that I'm very much interested in open science and education. So we have a YouTube channel where we teach quantum mechanics. So if you ever find yourself in need of directing a student or something to learn some quantum mechanics, these are short, like 5 to 30-minute videos, which cover topics. At the moment, it's mostly second, third year undergraduate level, but we're hoping to. There is also some second quantization in there and so on, so some more advanced topics as well. If you have any suggestions, then also feel free to let me know. And finally, these are my collaborators. So Bopeng is a PhD student working in Cambridge, who's done pretty much all the simulation work. And Robert, Jan, and Adrian are the two heavy theorists. We collaborate with them. They're the ones who sort of done all the heavy maths for this non-abelian braiding and so on. And they've been teaching us a lot of this. So anything that I have said that hasn't been clear is probably because I haven't yet understood it completely well from what they've been telling us. We have both of this. We have two papers out on the archive about these topics. If you want to learn more, and they go into much more detail about sort of the mathematical background in these things, and indeed how we build this global topological configurations and so on. So if you want to learn more, then you can find that there. And thank you very much for your attention.
Okay, thank you for this very nice talk. Any questions or comments?
In the analysis of these three groups of bands, are you still using the quaternion group?
So what we're trying to do essentially is we're trying to the frame charges are described by the quaternion group rather than going through I minus I, J minus J, which would be very complicated. Essentially, the Euler class, the Euler patch, and so on gives us an alternative view on that. That's more amenable to calculations and so on. But it is, yes, you can rephrase all of this in terms of these what we call frame charges, which are I minus I, J minus J, K, and so on. So just to give you a quick example of how they're related. Like this. So this is essentially the relation between the frame charges and the Euler class. So in a sense, if you want all our filled circles were plus J, or our empty circles were minus J because they were in gap 2, and all our filled squares were plus I, and all our empty squares were minus I.
But with more bands, you don't have these three.
Okay, so with more bands it's a bit more complicated, but essentially what happens is that between one band and one that's 2 away, all the frame charges commute. So you can still focus in groups of 3 bands, even within this larger subspace, and those groups of individual groups of 3 bands still follow this, and then between an extra band, they actually commute. So it's but you're right, and it is more complicated. We have more than 3 bands, and I won't go into that at all. But yeah, there's actually plenty to do here. So things that are not known, for example, is the bulk boundary correspondence. So we have actually done some surface state calculations, and we do see some interesting surface states, but we don't know yet how to fully characterize them. Response theory. So there are plenty of things that are still to be understood in these compounds. And one of them is also more than 3 bands. What really
More questions?
The silicon oxide material that you were showing. So you were showing some pictures like with the effect of strain on the phonon. Which is the particular strain that you are applying? Like in the actual?
There it's uniform. And what we have in mind, so in practice, so what we really want to do, that was the second example. What we really want to do is we really want to come up with an experimentally physical setup. So we can actually observe braiding if we change the strain of the system uniformly. But in practice, the way you would do that is the way you would apply strain, say, to the material is to grow it on a substrate of a lattice parameter that doesn't quite fit that, and then it forces the 2D compound to either shrink or expand to adapt to that. So that's something you cannot really manipulate. So you grow your sample on a particular strain, and that's it. You cannot just change the strain because you cannot sort of rebuild it on a different sample. So why we're using strain here is because without strain, for realistic electric fields that you can also get in the lab, then nothing really happened. So the bands were just too far away to actually have this band inversion and so on. So we applied the strain to essentially bring the bands together, and then with realistic electric fields, we can flip them. Now the strains may look quite large, like 5%. I think we have an example of 7%, but actually these are realistic in 2D systems. So in a 3D system, strain beyond like 1 or 2% is really unrealistic. But in a 2D system, people have actually reached strain of 20%. And for these specific compounds, there are people have grown them, I think, up to 8 or 9%. So it is definitely within the experimentally accessible regime for these compounds. But we use a strain essentially as a way to, if you think of it as a phase diagram, we use strain to go very close to the phase boundary between braiding and so on, and then we use the electric field to actually do the motion of the nodes. The other one, just with the gate voltage, if you want, that was without any strain. Just putting that there, gate voltage, and taking that. So we also did that should be simple. But here the braiding doesn't happen at the gamma point. So Raman doesn't work here to actually observe this.
Danny?
Is there some generalized Nielsen-Minomia theorem that puts constraints in the charges of the nodes?
So my answer would be, I don't know. We are looking at a variety of things to do with this. So one of the things I haven't talked about, the relation between these and other known phenomena. So one of the things we've been looking at, for example, is the relation between these and Goldstone theorem, because in phonon bands, you actually have, even in 2D, you have a 3-band crossing point for the acoustic modes at the gamma point, right? So the acoustic modes at the gamma point all go to 0. And that's in general given by Goldstone's theorem. So it's you have translational symmetry in your system. And we've actually, for example, realized that from the point of view of these ideas, because this sort of 3-band model. And we found some interesting connections there. So there is plenty to do. I haven't actually thought about this. So there may actually be an answer to this question, but I don't know it.
I may, I also have. Do you know how robust is this to many body interactions? Because in the electronic system, I mean, yeah.
Yeah, so I would say, I don't know. And I guess this is I think Maia may have some work actually for like single gap topology on how electronic correlations. I think I saw an archive paper from you recently. But I think it's a general question for topology in general, how correlations affect things. So this is all single particle theory. I have no idea here. And I think even in standard topology, if we want, I think this is still an open question. But I think you have some recent work on that.
Yeah, actually, it's the work of Mikkel. We try to apply, understand topological phases in uncorrelated systems as a function of crystalline symmetries, and we use the single particle Venus function. But I mean, if you have weak interactions in your material, which is the case of the materials he has shown, then you don't need to worry about the correlation.
Yeah, I mean, I see it clearly in the single gap topology because you only need that your ground state is adiabatically connected to the interacting ground state, or at least I understand it that way. But in the multiple gap topology, you also, or at least a sufficient condition would be that your ground state and the excited states that where the band crossings are in the other bands need all be adiabatically connected to the non-interacting ones, or maybe I don't know.
No, yeah, sure. I mean, if you have correlations, that's another story. But I think this approximation is not taking into account correlations. So we are in the single particle picture, and it's enough to do this braiding. So the moment you have correlations, then maybe the filling is not even an integer. You have fractional charge and things like that. So I guess you need another formulation to deal with this type of anionic exchange. Are there any more questions?
Are there any thoughts or expanding this to this multi-gap kind of topology to Hamiltonians that are not constrained to be real?
So this fundamentally depends on them being real.
So the quaternion charge appears when you
Yes, I haven't really gone through it, but if you're interested, I can very, very quickly give you a notion of how that comes about. So essentially, if you have a real Hamiltonian, a 3-band real Hamiltonian, then you have 3 real eigenvectors, and they form a 3D orthonormal frame. So 3 real eigenvectors. And you can describe them with an orthogonal matrix O3. Now, in reality, we actually limit ourselves to oriented frames. So fixing the orientation, the handedness gives you rotation matrices. And then we have this gauge degree of freedom that I was discussing, which goes from a phase gauge degree of freedom to a plus minus sign gauge degree of freedom. And probably just an example of how that works. So essentially, the order parameter space of the Hamiltonian can be expressed as SO3 modulo the group of pi rotations, which happens to be the dihedral group. And then you can characterize, that's what we call them frame charges, this frame, and that's where the mathematics of our colleague comes in, but I believe that the homotopy group happens to be the quaternion group. So it is fun, I think, at least in this context, it is fundamental that you have a real Hamiltonian to do that.
If you don't have, instead of SO3, you have SU something, that's what I mean, like, is that,
Yeah, so
that problem studied or
we haven't studied that at all.
Yeah.
So I'm not sure exactly, but this particular case, that depends on having SO3.
Okay.
And also, regarding just to whether I understand correctly the difference of the multi-gap thing, at the first part of your talk, when you were showing like some single gap topology in some, I think that there were some perovskites, there were some triple white nodes that you give them topological charge. But the thing is not like the number of bands you have in that model, but the number of gaps, no? So in that sense, you analyze that thing, you need a 3-band model, but you have either 2 degenerate bands above or below, no? I understand. So what's the difference?
So I think there are various ways to think about this. So I'm not sure if exactly that will address your question, but in some sense, this, for example, you can think of this also as a fragile topology, where you could trivialize everything with the 3rd band. But the difference with the usual fragile topology is that here you fundamentally depend on the 3rd band. You cannot describe this without the presence of the 3rd band. So that's no way to see that you have the 3 bands, that you need the 3 bands. What you're asking me is if I have
so I know because you saw a Hamiltonian, the simplest Hamiltonian of 3 bands, which is has like 3 fixed energies, and you could go from that Hamiltonian to a 3-band Hamiltonian with just 1 gap by making, if you have
okay, so you could make 2 bands degenerate essentially with an extra symmetry. So that could be, I guess, a special case of this. So we haven't actually looked much at, of course, then you can play the whole game when you have crystalline symmetries, for example, that force some band degeneracies,
Yes, yes,
how does that change? Yeah. So we've seen that to some extent in the sense that, for example, they tell us that we have, rather than two nodes, copies of nodes, and nodes move along high symmetry lines and so on. So what you're saying is, if we have some symmetry that for the entire Trigonal zone forces two bands to be degenerate, then how you can think of, is that your question essentially?
No, the first part of your talk, you were talking about well nodes in phonon bands, but in your picture there were also appeared triple well nodes, which are crossings of three bands in the picture. I think, if I'm not mistaken, at the first part of your talk. Wait. Yeah, there is something that triple well bond. So you have three bands there.
Okay, yeah.
So that's, you need a three-band model to understand.
Okay, so we haven't actually looked at this in that context at all. So here, all we have really is we have, I think this is symmetry and forced crossing points. So we essentially have, in this particular system, I think we have two mirror planes like this, here and here. So on those two mirror planes, the crossing points become nodal lines. And then I think it's a combination of, I can't quite remember, but so don't quote me on this, but I think it's C4 symmetry and the crossing of mirror planes that leads to this extra nodal line here as well. And then they happen to cross triply here and here. So we actually analyze this from the point of view of symmetry in this case, and that was enough for us to understand that. So we're trying to say is we could reanalyze this in terms of the three-band topology and see what happens. I mean, in principle, the problem here is that the three bands are not isolated. So it wouldn't, I think we would need much more than that to understand it, because then you go somewhere else and there are more bands coming in. So you can't just define all these things that we've played around with. We really need these three bands to be isolated to be able to define all the frames over which we calculate these things and so on. So from that point of view, we haven't looked at it.
Okay.
Just by curiosity here, the calculation of the phonons you're doing with adding just electrons artificially and solving by frozen phonon or something like that.
So yes. So given what you're also interested in, so this is of course a phase that has imaginary modes,
right? Yeah,
usual. Yeah. So we actually did calculate this also at finite temperature. And when it becomes stable, and we found some interesting crossing points. Here we don't need with photoexcitation, we don't need temperature to stabilize it. Actually, this was first proposed by somebody else, like a year before we did this. That you can stabilize it with photoexcitation.
Yeah, I've seen this. Yes.
Yeah. So essentially what we did is that we just did this, what is it called, delta CF maybe, where you remove an electron from the valence band and you put it into the conduction band. The reason why we decided to focus, so we actually studied this here with various external parameters. We used the strain, we used temperature, and we used a few others. The reason why we focused on photoexcitation is because these materials have relatively large LLTO splitting in the gamma point. And essentially, LLTO splitting means that the bands move away from each other. So that sort of suppresses crossing points. When we have photoexcitation, we have some free carriers here. So that screens the long-range interactions. So it suppresses LLTO splitting. So that promoted crossing points.
I see.
So in a sense, the story could have been told similarly with using strain as tuning parameter or using temperature as tuning parameter, but it was nicer if you want using photoexcitation because we had many more crossing points. And we could discuss a bit more the interplay between mirror symmetries and nodal lines and so on and so forth, just because of these free electrons that screen the long-range interactions. But from a computational point of view, that's literally all we did. One could probably try to do this better, but that's how we did that.
Okay. Are we
One,
done?
if I might.
Yeah, sure.
Can you break nodal points in 3D, or you need lines?
So
here, because you were discussing here 2D systems, right?
yes. So what you need in this context is a real Hamiltonian, and the conditions are those there. So actually, the example we have for electronic systems, so with So this is also a piece of work that we have on the archive at the moment. So this is for electronic system. This is a 3D system, and all the braiding happens. All the 3-band real Hamiltonians are on C2T invariant planes within that 3D system. So in this particular case, I think it's the Trigonal looking system. So the Brillouin zone has this shape here, and we have 3 C2T invariant planes, which are, I think, the horizontal plane here in sort of bluish, and then this one here and this one here. So these nodes are forced to be on those planes by C2T symmetry. And what was interesting about this piece of work is actually we see the nodes going from one plane to another when they hit the boundary between planes. And actually, it was what we think is interesting about this work. I haven't gone into that at all. Is not only the non-abelian braiding that happens as you, in this case, as you essentially go from this structure to this structure, which experimentally it seems to have a temperature-induced structural phase transition. But like there is a very narrow temperature range where there is an intermediate structure experimentally. So it looks like the structure is smoothly evolving from one to the other. And because the potential energy surface looks like this. So you have a high temperature phase here. And then as you lower temperature, you have first this phase and then this phase. They almost have the same energy. And there is this sort of a very flat potential connecting them. And experimentally, they seem to be able to get the structure stuck somewhere in the middle here. So essentially what we're showing there is the evolution of the Val nodes of the crossing point as you go from here to here. And what happens is that because of the symmetries of these two structures, the nodal point actually need to go from one C2T invariant plane to another. And therefore the Val nodes with a very small change of external parameters of like 1 or 2 Kelvin, they have to travel a huge distance in the Brillouin zone to obey the symmetries of the system of the starting and final points. So not only do we observe this non-abelian braiding, but also the Val nodes travel like almost half the entire Brillouin zone to accomplish that. So it's like, yeah, we thought that was interesting from that point of view. But yeah, it can definitely be embedded in 3D.
But when you are constrained somehow to the plane where you have real Hamiltonians.
Yes.
Okay, more questions?
So all this braiding happened. I mean, in the examples that you saw, the bands were more or less close, right?
Yeah.
So the gaps between the bands in the non-occlusion regions were close. So this works still if if there was a bigger energy difference between the bands.
So eventually, so I guess you would need a larger, like the band should respond to that. I'm not sure if I completely understand your question, but essentially you're saying that if the bands are very far away, then can you actually make them interact to do this braiding? And I guess essentially you would need the bands to respond very strongly to whatever external parameter you're tuning to actually be able to make them interact with each other. So in a sense, we found that difficult. And that's why, for example, in the second case, we had to apply this strain to bring the bands together to actually see that. Is that roughly what?
Yes. So but what I was wondering is why the crossing of 2 bands and then another crossing of a different set of bands.
Oh, I see. I think you say if the slopes of the bands are very large.
Yes.
I guess that would be possible. So yeah, so I can understand your question better now. So what you're saying is that if the bandwidth of the 3-band system was very large, but you still had crossings between the bands,
yes,
and that could be because the slopes of the bands are very large and so on. So I guess in principle, the answer would be yes. In practice, I guess if the slopes are very large and the bandwidth is very large, and likeliness is that you're actually going to cross with other bands. So it may be harder to get an isolated 3-band system, like what we had, like with that very clean, just 3 bands separated by a large energy gap from other bands. So I mean, in principle, of course, you can always bring more bands and things become messier. Here, we actually have more than 3 bands. So things are much, much messier. But people having observed this experimentally on real materials, they have observed this in some like metamaterials and so on. Not the braiding, because every metamaterial is like a parameter in there. So you have observed these frame charges, and then have to build a different metamaterial for each configuration. So not the braiding. But so the initial aim is just now to observe this. And we think for that, you probably just want a set of 3 isolated bands. But yeah, in principle, it's like standard topology. You could describe, very curvature solution with two-band model, and in real system you have tons of other trivial bands or whatever in there that just complicate the analysis somewhat. So I guess that's what would happen if you had a very large bandwidth for the three bands of interest. That line is that they would cross with other points with other bands.
Okay. Wait. If anyone on Zoom has a question, unmute yourself. Okay. Then let's thank Bartomeu again